Hello, I'm Danil. This is now my math and chess channel. This is the first math video I'm going to do. I just got my blood drawn and I felt like doing an integral. I've had this one in mind for a while. Anyway, we have our integral generalized for 4 parameters, because why not? So we have integral from 0 to infinity of x to the a times e to the minus b x to the c times sine dx to the c times ln x dx. So yeah, looks pretty gnarly. Here are some conditions that I think have to be satisfied. I could be wrong on some of these, so feel free to correct me. I'm a high school student, so I don't know anything, right? So yeah, A can't be -1, B, C, and D can't be 0. Although maybe they can. Maybe everything just collapses to 0. And then yeah, I don't know if this only works for real numbers, but I don't want to take the risk and say that it works for complex numbers when it in fact might not. So yeah, and then this fraction, the negative of this fraction can't be an integer, or in other words, this fraction cannot be a negative integer. I wonder where this is going. And this lovely red box here I drew because I know my light is like making an imprint on the board, so I tried to outline where it was to tell myself where not to write. And it works well to put my eraser there. So all works out. Anyway, let's talk about how to tackle this thing. Oh, actually, first, I do want to say the structure of this resembles a Maths 505 video, which it was inspired from, except I'm pretty sure it was cosine, if I'm not mistaken. Except it only had these 2 terms. So, and it was generalized for a few parameters, but not 4. I think it was 3. Anyway, so my idea was, let's take that, throw in an x to the a, throw in an ln x, and that should make it a lot more difficult and long, but at least then it's unique. So yeah. Anyway, now let's discuss how to approach this. So the first thing that stands out is this ln x, because it's sort of free of any parameters. It's just there. And the first thing we should think about is how, can we just get rid of it? Which, of course, we can, because if we look at just this integral, if we ignore the ln x, scoot the dx back in, this integral right here, if we took that, differentiated it with respect to a, we'd get x to the a for that term. So everything would stay the same, but then we'd throw in an ln x. So the idea here is that we could take that integral, everything that doesn't have ln x in it, find some closed form to represent it, and then differentiate that with respect to a, and then we'd get our target integral without having to actually straight up evaluate this entire thing, because that would complicate things, to say the least. Is that it? Yeah, okay, I think that's all the introduction we need. So yeah, let's get started. So like I said, we're looking at this. This is a fresh Expo marker, by the way. So it's gonna hopefully not fade away like some of my other markers. I've used them for a while, so no hate, no disrespect to them. Anyway, yeah, so we have x to the a, e to the minus b, x to the c, times sine of dx to the c, dx. This d here is always going to make it look funny with other variables because it's going to look like a dx. It's not an infinitesimal, it's just, I wasn't going to make my variables or my parameters a, b, c, e, because that would be stupid. So you're just going to have to live with it. So yeah, this is what we're looking at. We're trying to find some form for this and differentiate it with respect to a, and then boom, we'll be done. And unlike the normal situation where you use this trick, we don't have to input a number at the end because we already had just a parameter there. Like, it's not like this is a 1/2 or a 1/4 or something. So we just get to leave it as it is. No need to plug anything in at the end. So anyway, now we got to figure out how to simplify this. So first thing that should come to your head is to get rid of the exponents in the arguments of the exponential and the sine function. So yeah, that's easier done than said. Let's make let's set x to the c equal to u, so that at least we can remove any sort of pesky exponents inside any arguments. So this means that u to the 1/c is x, so then we differentiate both sides. That would give us dx is, so we have to use power rule, so we're going to have to multiply by 1 over c. So I'm just going to do an over c, and then subtract the power by 1. So it's going to be u to the 1 over c minus 1. Yep. So, and this just came from x equals u to the 1 over c. So then we can, excuse me, we can rewrite this in terms of u, and the bounds won't change, because when x is 0, u is also 0. When x is infinity, u is also infinity. So that's convenient. Anyway, so what's x to the a in this world? Oh, I should say, this 1 over c I'm just going to put in the front, because there's no need to keep it on the inside. It's just a constant. So x to the a. We established that u to the 1 over c is x. So if you raise both sides to the 8th power, you'll have x to the a equals u to the a over c. So that's what we're going to have. We're going to have u to the a over c. Also, I'm going to have to occasionally check my phone just to make sure it's still recording, because I'm sure technical difficulties can happen. Anyway, so that's what our x to the a turns into. Then we have e to the minus b u. And then we have sine of du. Not sine of an infinitesimal. But, and then our, there we go. Knew I was forgetting something. Okay, so then our du is going to have that 1 over c attached to it, which we already dealt with. But now we're just going to have to stick in a u to the 1 over c minus 1 du. Okay, so that's what we have now. We can combine some like terms. So I'm also going to start erasing things just so I don't have to use as much board room, because it's going to definitely take quite a bit. So anyway, we have these two u terms, and we're just going to have to add their exponents since they're being multiplied. So in the end, we're going to have u to the a over c plus 1 over c minus 1. So we can also rewrite that by doing u to the a plus 1 over c minus 1. So that's what I'm going to do. I'm just going to shift everything. Ooh, okay. I got to rewrite that. Bear with me, folks. I'm not a professional YouTuber. Almost. Better. Okay, so that's what this turns into. Yeah, so that's our polynomial, or our u now. That's the power it's raised to. But now I think the next step should be pretty simple if you've worked with these kinds of structures before. We have a polynomial, or gosh dang it, just okay, I'm just gonna call it a polynomial, and an exponential. So that automatically should like get you on the track. Is there a way we can, I don't know, get rid of this and maybe turn it into an exponential itself? Yes, of course. So I'm sure anyone who's watching this probably already knows, but just for propriety, I'm going to say it. E to the I theta is cosine theta plus I sine theta. And here, this part right here is the imaginary part of e to the I du, because e to the I du would be cosine du plus I sine du. So, and this is the coefficient of I, meaning it's the imaginary part. So that's what we can do. We can change this, and the imaginary part is a linear operation, so we can just pull it outside of the integral entirely. But I am going to keep the, yeah, we don't have any room. I'm going to keep the 1 over c out front, because it's just a constant. It's not going to change the imaginary part of whatever. So we're going to have the imaginary part of the integral from 0 to infinity. We're going to have, we still have u to the a plus 1 over c minus 1. Then we're going to still have our e to the minus b u. But then remember, we're replacing this with e to the du. So now we can combine the e's. And we'll get e to the minus bu plus diu, but I'm going to factor out a minus u out of that, which will give us e to the minus u times b minus di, because we have to introduce another negative. So that's what I'm going to do. Keep forgetting I made a handy spot for that. So e to the minus u, and then we're going to have b minus di, and then du. So boom, that's what we've got. Now we've managed to remove this trig term and make this into a much more wrangleable integral. And now the next substitution is also pretty intuitive, because if you knew where this was going in the first place, but if you don't, I won't spoil it. We're gonna make u times b minus di equal t, just some other variable. And then if we divide this, and remember, this is just a constant, so I'm just going to divide this over, and we can do du equals dt over b minus di. Yep. So, okay. And so what that's going to do is it's just going to change our exponential term to an e to the minus something, some variable, without any extra additional constants in it. So how's that going to change our integral? So we have a 1 over c times the imaginary part. Now, the differential term is going to have a b minus di in the denominator. So since that's a constant, we're just going to pull it out front like this. Save us the time. And once again, the bounds are unchanged. As u is 0, t is 0, u is infinity, t is infinity. Okay, but what is u? What is u in the t world? Well, if we divide by b minus di, you'll have u equals t over b minus di. So that's going to give us t like this. And then our exponent is just a power once again. So, or sorry, it's just a number because they're all constants. Like that. And then we have e to the minus t dt. Okay, and now this b minus di to this whatever, we're going to be able to just pull that out. So it's in the denominator. And fortunately, our other term is in the denominator too, so we'll keep it that way for now. So we can change this term into t to the a plus 1 over c minus 1 over b minus di to the a plus 1 over c minus 1. And then we can pull that, the term we're dividing by, out in front. And since we already have a technically b minus di to the plus 1 out here, this is going to cancel out this extra negative 1 right here. And on the outside, we are just going to be left with b minus di to the a plus 1 over c. And then we can get rid of the extra stuff here. So you're going to have t to the a plus 1 over c minus 1. Okay, look at that. So keep in mind, these are all constants. So that means this integral, since it has only one variable in it, which is what we're integrating with respect to, is just going to give us a number. And you may recognize this, which was kind of the whole point of doing it this way. This is the gamma function. And our power is a plus 1 over c minus 1. But when we write the gamma function, we've got that shift of plus 1. So that plus 1 is going to conveniently also get rid of that, so I just won't have to write that again. Yeah, so this entire thing, because remember, it's just going to give us a number for whatever we plug in for a and c, which they're just our parameters. So this, all of that, we do not have to see anymore. We just do gamma a plus 1 over c. And now the idea with this restriction is quite obvious now, because the gamma function is not continuous at negative integers. So yeah, that's why we don't want this fraction being a negative integer. Look at that. Okay, so now we can also rewrite this again, because the gamma function here, it doesn't have anything imaginary in it. It's just a constant right now also. So the imaginary part isn't going to change this at all. So we can move that outside of the imaginary part operator, which will just give us this. And then imaginary part of 1 over b minus di to the a plus 1 over c. Okay, so now we've just got to settle this imaginary part thing. So I'm going to only take this, this little term right here. That's what's going to be moving to the next line, just because I don't want to have to rewrite this every single time. So we're just going to manipulate this until we find a way to find its imaginary part, which isn't very difficult. So first of all, let's notice that this is, what is it? Since it's 1 over something to some power, we can just remove the reciprocal and just put a negative sign out front, as long as we negate the entire fraction that we have as a power. So that means, and again, remember, I'm only writing this little part. So the 1 over b minus di to the a plus 1 over c is just going to be b minus di to the negative a plus 1 over c. Like that. So this is what we're dealing with, this expression. We want to find its imaginary part. So I know there's a couple ways to do this, but I always stick with the same method each time. It's a lot of words. So first, we're going to show that this is equal to e to the ln of b minus di. And then all of that raised to the minus a plus 1 over c, because this stuff should cancel out, and that gives you your b minus di. But we can use our rules for complex logarithms here, which I'll just show. So the ln of a complex number, which I don't know if you're supposed to write it as log or something, but anyway, you have to do the ln of the modulus of that complex number, which would be the square root of the imaginary part squared plus the real part squared. So like the distance formula, basically, because that's what it is. And so our imaginary part of this expression is minus d, but square that and the negative goes away. And our real part is b. So our complex logarithm is going to have, I didn't finish my statement. We have b squared plus d squared. That's our first part of this. And then you have to add I times the argument of that complex number, which normally we can't just, normally you'd be able to find the actual value, but since we have a bunch of parameters here, we have to solve it like with the actual formula. So, and the formula for that would be the arctangent of the imaginary part over the real part. And remember, our imaginary part here is the coefficient of I, which in this case is minus d, and we have b as our real part. So that means we're going to have plus I arctangent minus d over b. Imaginary part, real part. And then all of this is still being raised to the minus a plus 1 over c. Okay, so now we've got that. Now we just have to distribute this term right here, this power, into this, and then we'll see what happens. So this will give us e to the negative a plus 1 over c ln of this plus, oh wait, no, minus a plus 1 over c times the arctangent of negative d over b. Now, I'm going to save us some time here. Very little, but whatever. Arctangent's an odd function, so the fact that we have this negative, this negative 1 coefficient for d, we can pull that out, which will make the arctangent of something the negative arctangent of the negative of that something, which in this case is just positive, and that'll just cancel out this negative we have out front. So we can make this disappear and put a plus. So yeah, that'll just, I don't know, it's just nicer looking that way. And now we can split this. So, but first let's pay attention. We have, with our log properties, we can bring this coefficient to as a power of the argument. And keep in mind, we already have a power in our argument, which is 1/2. I just didn't pull that out because we're going to need it right back. So if we have a 1/2 there and we put another power on top of it, we're just going to have to multiply those two powers together to get the power that we're looking for of our argument, which all that's going to do is put a 2 here. Since this fraction right here times 1/2, we just put a 2 right there. And then once that happens, we've freed ourselves of any coefficient of ln, which means we can just cancel out the e and the ln, which will give us b squared plus d squared to the minus a plus 1 over 2c. And then we still have e raised to this power, because we can just multiply them, remember? Because we had the terms in the exponent were added, so we can just multiply them. And then that's what I did, and I canceled out the e to the ln. And boom, we have this term right here, which once again is just a constant. So that one's, we're not going to care about that with the imaginary part. But we shouldn't forget this, because that's bad form. So now we got to figure out, oh, hold up, I'm missing something. Yes, okay, there should be an I here. I made an error some time ago. There should be an I in this argument. Yeah, just from this thing. Yeah, it's been a long day. So yes, we should have an I here, because otherwise this would just be a real number. So then we have to expand this again. So remember that e to the I times something is cosine of that something plus I times the sine of something. Well, that something. That's just me trying to use variables. Anyway, so that means this would be cosine of all this stuff. So just look at everything in the power excluding the I, and then plus I sine of that same stuff. And now, since we're looking for the imaginary part, the sine function is what's going to be the imaginary part of that. So that means if we just replace this entire thing with sine of this fraction times arctangent d over b, that would settle our imaginary part, because that was our imaginary part of the only thing that has an imaginary part and a real part in this entire expression. So now that means we can change this to sine of a plus 1 over c times arctangent d over b. Okay, great. So now this thing has been turned into this thing. So now let's establish what we have. We have 1 over c times gamma a plus 1 over c. And then this stuff. So we have b squared plus d squared to the negative a plus 1 over 2c, and our sine function. Okay, so yeah, this is our expression that we have after all that. We've settled the imaginary part. This should just give us a real number if we plugged in stuff. So that means we're done, right? Yeah, no. Remember, this solution here only works for this integral. That's the one we were working with in the first place. Well, not in the first place, in the second place, but whatever. So the idea was to differentiate whatever form we had with respect to a. So now you see it's going to get a little more ugly. But yes, if this was our target integral, this would be our final solution, because we've resolved everything that needed to be resolved. But we haven't with our target integral. So now we have to differentiate with respect to a, which is going to be a little bit tedious, because we have three functions that have a somewhere inside of it. But just got to get cracking, I guess. So let's put this away. Now, it's going to be, the only thing that's going to be annoying here is juggling all the parameters. So bear with me if I have to, like, you know, turn some gears. Anyway, so I'm just going to write, we have d by dA. Okay, so our 1 over c is just a constant, so we're fine. Let me check camera. Okay, so that thing's not going to matter. We're just going to pull that out. Now we're going to have big parentheses, or parentheses, whatever. Okay. Now, when you have 3 functions and they're multiplied together, basically you could, what I used to always do was that I, differentiate one, keep the other 2 terms the same, and then keep that first term the same, and then do the product and multiply it times the product rule of that, which, well, of the other 2 functions, which does work, but it's simpler if you think about it the other way. So, which basically is you differentiate each one separately and multiply it by the other 2 original functions. You'll see what I mean. Or you probably already know what I'm talking about. So first, for the gamma function, we're going to have, when we differentiate the gamma function, we just write gamma prime, so that's fine. But by the chain rule, we're going to have to multiply this 1 over c, because that's our coefficient of a. We can split this as a over c plus 1 over c. The 1 over c differentiated goes away, and the 1 over c is our coefficient of a. So we have 1 over c, gamma prime, a plus 1 over c, and then we just keep everything else the same. So we're going to have b squared plus d squared. We're going to need another line, by the way, as you'll notice. So we have minus a plus 1 over 2c. Yep. And then sine of this. Okay, so that's our first term. Now, next, I'm just going to put ... Now we're going to differentiate the second term and keep everything else the same. So now b squared plus d squared is a constant, and we're raising it to our variable exponent. So the derivative of that is going to be keeping this the same, just keep this term, times ln of this. And then, of course, by the chain rule, we're going to have to multiply by the derivative of our exponent. Yeah, so let's get to it. We're going to have b squared plus d squared, plus d squared, all still raised to the minus a plus 1 over 2c. Okay, and then we multiply by the natural log of this, of the base. It's a weird angle to write at. And then by the chain rule, if we split this up, we'll have negative a over 2c minus 1 over 2c. The minus 1 over 2c goes away upon differentiation. And our coefficient is just negative 1 over 2c. So I'm just going to put negative 1 over 2c. Yep. Okay. And then we have to, since that was just the derivative of the term, we have to write everything else as well, which is going to be gamma a plus 1 over c times sine plus 1 over c arc tangent d over b. I'm going to stop saying it because you're going to hear me say it a lot. Anyway, so that's our second term of the big product rule. So then now finally we have to differentiate the sine term and keep everything else the same. So the sine's going to turn to cosine, we know that. But for our chain rule, our constant, again, if we split it up, you'll get that the coefficient of a is arctangent d over b all over c. So I'm just going to do that. We have to do plus. It takes out a lot of breath. So we have arctangent d over b over c. And then we have cosine of the same stuff. Yeah? Okay. And then we keep everything else the same. So we'll have gamma a plus 1 over c, and write this b squared plus d squared to this power. Okay, and that should be our entire expression. 1 by c is multiplied by all of that. So that's our closed parentheses. I tend to miss parentheses occasionally, so I'm just checking. Yep, okay. You see what I mean? I just have to go back and make sure we're good there. Yeah, we're fine. Okay. So yeah, this is our function. That's basically our final answer, but it's just not cleaned up. So that's exactly what I'm going to do. I'm going to clean this up, and we should be done. But of course, I'm going to write it in black to match our starting problem. And I have to actually kneel because it's such a strange angle. Okay, so we have our final answer of I as a function of a, b, c, d. Let's change this. Equals. Now, let's see if there's anything we can factor out. Let's just go one at a time. Okay, so first thing we see is a 1 over c. Does every term have a 1 over c? This one does, this one does, and this one does. So yes, we can factor out a 1 over c. So I'm just going to put that along with our original 1 over c. So that's going to be a 1 over c squared. Now, is there anything else? Not all of them have gamma prime, we know that. Do all of them have this? Okay, so we have that. We have that here. And we have that here. So yes, we can in fact pull that out. So I'm just going to put that up here. Okay, great. Not all of them have a sine term because we know one of them turned into cosine, and not all of them have a cosine term because we originally had sine. So yeah, now we're just going to have to write everything else. So big parentheticals here. Okay, so let's start off. We have gamma prime a plus 1. Okay, that's not going to cut it. Okay, so here, when we factor out this and an extra c, we have gamma prime of this times our sine function. Okay, next we have, this is already factored out. This remains, but the c is gone. So we actually need to do a minus instead of a plus, right? Yes. So minus ln of b squared plus d squared times gamma a plus 1 over c. Just making sure. We needed a 1/2, didn't we? Yes. Okay. Just making sure we're on track. Yep, okay. And then just times sine of the same stuff. And then finally, we have this, factoring out that and this term gives us just our arctangent term. And, oh, our cosine. Okay, so I might need to use another line. So, okay, yeah. We'll just move this to the next line so it doesn't look too horrible. So we have plus. And what do we say? Just the arctangent. No, don't fade on me. So close. Okay, the arctangent, and then we just have our cosine and gamma function. So we're going to have cosine of all the same stuff. Becomes easier to write once you've written it a million times. And then gamma, a plus 1 over c. There's another missing parentheses. Is that it? Got that. All right. So, after this entire journey, we figured out that our original integral, parameterized with 4 parameters, variables, whatever, is equal to b squared plus, no, I'm just kidding. I'm not going to say all that. Yeah, I mean, of course, you're never going to run into a generalized version of this. You probably won't run into any form of this. But if you ever do, and you don't have a calculator, you don't have WolframAlpha, you don't have a friend, you don't have a teacher, you don't have a textbook, you don't have an answer key, whatever, you can just plug all your numbers into this beauty and you'll get your answer. Yeah. And I might have done something wrong. I don't know. I'm going to go check it with WolframAlpha, and if it all works out, then I'm going to keep the video up. And if not, feel free to tell me in my comments that I screwed something up, because there's a good chance I did. Yeah, well, as I said, it's hideous to look at, but it is pleasant after doing like a half-hour math video on it. So yeah, hope you enjoyed. This is the first of many.